then we're going to do another example. This one bringing back a shape that we've worked with a lot. So we're going to evaluate surface integral for f equal to x squared, xy, x cubed, y cubed over the surface of the tetrahedron bound by x plus y plus z equal 1 and coordinate planes. Oriented outwards. And so what we're looking at is this same. So we should be used to thinking about this plane x plus y plus z equal 1 kind of forms a triangular wedge when you cut it through with the xy plane, xz plane, and zy plane. But now we're also thinking about these surfaces too. So we're thinking about this triangular part that usually we work with, but it's a closed surface. It's a geometric object. And so this little triangle in the xz plane, this triangle in the zy plane, and this triangle in the xy plane are also part of your surface. And so it is closed. And I'm going to get rid of all those lines because I think they make it harder to look at. So surface is closed, f is continuous. We can go ahead and use divergence theorem. Oh, my computer just froze. Apparently disagreed with my strong statement that it's the best approach. So our divergence is del dot f. So we're going to look at d dx of the first component plus d dy of the second component plus d dz of the third component. Partial derivatives coming back for us. D dx of x squared is 2x. D dy of xy, x is a constant as far as y is concerned. D dy of y is 1, so we'll just get plus x. And d dz of x cubed y cubed is just 0. So we get 3x. And then we want to think about the 3D version volume that we're trying to integrate over. And so this is going to take us a little bit more space than what's available to solve for, but I'll go ahead and rearrange at least. This is z equal 1 minus x minus y is the equation for our plane. So we know that 0 is less than or equal to z is less than or equal to 1 minus x minus y. And then we're left trying to find the bounds of integration for this thing. Where the plane 1 minus x minus y hits the xy plane. So that's just the line y equal 1 minus x. Which is going to kind of go 0 to 1 on the y-axis, 0 to 1 on the x-axis. If you're not convinced that this number is 1, just 0 equal 1 minus x gives us x equal 1 right there. You all have set up this integral a bunch of times, so we know that the bounds of integration are that z goes from 0 up to the plane, and then y goes from 0 up to the line, and then, and then x goes from 0 up to 1. And so now we have everything we need to use divergence theorem. That surface integral we were asked to find is actually a triple integral, bound from 0 to 1 minus x minus y, 0 to 1 minus x, and 0 to 1, where I've picked order dz, dy, dx to write those bounds. There's more than one way to do it. And then the divergence that we have to plug in is just this 3x.